All right, this is the Nature of Science video and ask the question, what is science? All right, so let's just go ahead, jump right in. The first thing we did was the black box experiment. So in this experiment, you were given a box, and you shake that box, and you're trying to figure out what's inside that box. So we'll go over what the significance of that is, right? So try to answer the question, what is science? So science, right? So if you look at the definition of science we will use in this class, science is a self-correcting process, a way of doing things, of recognizing and detecting patterns in nature and describing these patterns. So science, like the human mind has evolved to recognize patterns. Like we are pattern seekers. So if you look at that photo off to the right, you'll notice that it looks like the Mona Lisa, but it's just a bunch of photos combined together. This photo, I mean, it's just a bunch of splotches, but if you look, you can see a dog um, that looks like it's going away and it's sniffing the ground. In this one, you can see that there are two faces together, or it looks like a vase. So our minds are really just tuned to see these patterns, right? So here's another one. Let's take a look at these numbers, right? So 0, 1, 1, 2, 3, 5, 8, 13, 21. So the next number is going to be 34. So that's the Fibonacci sequence. And the Fibonacci sequence, that pattern occurs in nature all over when it comes to flowers or pineapples or music. And it's known as it comes up with the golden ratio. And what you get is you get this spiral. And there's a lot of spirals in nature follow the Fibonacci sequence, right? And that golden ratio. So the nautilus, right? So if you notice the nautilus, that does follow the Fibonacci sequence. So science is all about pattern recognition, but not all pattern recognition qualifies as doing science. So let's take a look at the black box experiment. So the first thing that you did was you were going to do 5 different tests. Well, what you should have done is before you even picked up that box, you did a test on your own. You looked at it and like you don't know what's inside that box, but you should have been able to say a lot of things that are not inside of that box. Like, a minivan's not going to be inside that box, a lawnmower, a whale, an airport. Well, the next thing you did was you picked up the box, and you could say, well, you know that there's not something heavy in that box. There's not gold bars. There's not like a full water bottle, like based on its size. So you still have no idea what's inside the box, but you're continuing to narrow down what is not inside the box. Then you can shake it, then you can roll it, then you can roll it, do whatever, right? So based on the test you performed, what do you think's in the box? So explain your answer. Why do you think that is inside the box? Now, could you ever be as 100% certain as to what is inside the box without opening it? So we'll go back to this question a little bit later. Now, in your own words, how is this black box experiment similar to science? So let's take a look at that, right? So if you did this experiment and you think, well, how confident are you that you correctly identified what's inside the box, right? I would like, if you were like 100%, right? If you said you're 100%, would you be willing to bet like $1,000,000 on it, right? If you're not, then you're not 100% confident. Now, what would you need in order to be 100% certain what is inside the box? Well, you need to open the box. You need to actually open the box. But, well, you're not going to. You're never going to know what's inside the box. Now, the black box serves as a metaphor for science. So, this is why in real life there is no physical box that can simply be opened to reveal what's inside. That's like that answer. That's how the black box experiment is a metaphor for science. In science, nothing is ever known for certain. Science cannot prove anything correct or true. Science only provides a description of patterns found in nature, and that description is based upon well-tested hypotheses, and the experimental results are reproducible and verifiable by anyone. So here's the idea behind it, right? Science can never prove anything true or correct. Science operates under one principle. It is known as the principle of wrongness. For a claim to be scientific, there must be a test for wrongness. Now, being true or correct and being not wrong are not the same thing. Being correct and not wrong are not the same thing. In science, there is no such thing as true or correct. You're just not wrong yet. So let's take a look at some scientific claims. If we look at this claim, right, blue light increases vegetative leaf growth. Well, is this a scientific claim? Well, yes, it is a scientific claim because there is a test for wrongness, and you can do this at home. Let's take a look at this scientific claim. Atoms are made up of smaller particles. Well, yes, it is a scientific claim because there is a test for wrongness. And we know about the proton, we know about the electron, we even know about quarks. Now let's take a look at this one. Avengers Endgame is the best movie ever made. Well, this is not a scientific claim. This is not a scientific claim. Opinions are not scientific claim. There is no test for wrongness, right? Opinions are just not scientific claims. What about this one? Ghosts exist. Is this a scientific claim? Well, no, it's not, right? This is not a scientific claim. Statements dealing with the paranormal or afterlife are not scientific claims. The absence of evidence isn't the evidence of absence, right? There is no test for wrongness for this. What about this one? The earth is flat. Is that a scientific claim? Oh, yes, it is. It just so happens to be a wrong scientific claim, right? Yeah, there is a test for wrongness. What about this one? Finding a four-leaf clover will give you good luck. Is this statement a scientific claim? No, this is not a scientific claim, right? Statements dealing with superstition or luck are not scientific claim. There is no test for wrongness. What about this one? Consuming margarine in Maine increases your chance of getting a divorce. Is this a scientific claim? So if we look at this graph, you can see here that the divorce rates in Maine seem to follow the consumption rate of margarine. Well, no, right? This is not a scientific claim. Correlation does not equal causation. There's just too many variables in this one to say that they affect each other. There is no test for wrongness. You can't get couples and have one consume few consume margarine and others not, and say, well, that caused the divorce rate or didn't cause the divorce rate. All right, here's some final thoughts. Right, science is not about who is right, but rather what is right. There's no room for human ego. Just because you want something to be true doesn't make it so. It is not about accepting things on authority. You must question everything. So let's look at an example. Can you explain the world's greatest physics demo? So then there's a world's greatest physics demo. It's just dropping a penny, just holding a penny out and dropping it. That's it, right? So could you describe that? Now, a lot of people would just say gravity, but what I wanted you to think is what Richard Feynman says. You can know the name of a bird in all the languages of the world, but when you're finished, you'll know absolutely nothing whatsoever about the bird. So let's look at the bird and see what it's doing. That's what counts. I learned very early the difference between knowing the name of something and knowing something. So saying the word gravity doesn't explain just dropping a penny. It's just a word, and it doesn't explain why the penny falls. So let's take a look at the ancient Greeks real fast, right? So if I dropped a penny, or if you dropped a penny, the ancient Greeks, like this is how they would have described it, right? So they thought that earthly things were composed of only those four elements: fire, water, earth, and air, right? These four elements had a natural resting place, and everything on earth wanted to be at rest. The more the material an earthly element was composed, the heavier it weighed. So the more earthly material, well, it weighed more. Weight was just a measurement of the tendency of the body to stay at rest. So what happens is you pick an object up. Well, you can feel that weight, and they thought, okay, well, because it's made of that more earthly material, it wants to be at rest more, so it feels heavier, right? And there exist two types of motion: natural motion, so straight up and down, because the object that would seek their natural resting place, right? So if you drop an object, it falls straight down. It wants to get to rest. And two, violent motion, imposed motion, because it is the result of forces such as a push or a pull. So I pull something, well, I let it go. That object wants to go to rest, right? It wants to go to its natural resting place. So if you drop objects of various weight, this is where they thought heavier objects being made of more material return to state of rest faster than lighter objects. So they said, okay, well, heavier objects fall faster than lighter objects. They want to come to rest. Well, is that a scientific claim? Well, it is a scientific claim. You can test for wrongness. So if you hold out a ball and a piece of paper and you drop it, the ball is going to hit the ground first, right? And it weighs more. Well, did you prove the Greeks wrong? No. Well, did you prove the Greeks correct? No, right? And you cannot be correct in science, right? You're just not wrong. Now, here's a simple test. Do that same test again, but hold the ball and crumple up that sheet of paper and drop them. Well, that piece of paper is going to fall faster because it's not doesn't have as much air resistance. So essentially, well, great. Now we proved that Greek's wrong, that part. But there was also another problem. Well, why didn't the moon and planets fall to Earth in a straight line? Why did they move in circular orbits about Earth? Well, here was their claim, their hypothesis. It was another assumption. There must exist a fifth element. They called it quintessence. So there exist two realms, right? Two separate rules. Number one, the earthly realm, where natural motion was a straight line, and the heavenly realm, where natural motion was circular. So were they wrong? Well, I mean, no. If I drop an object on Earth, well, it's going to fall straight down. If you look at all the objects that we can see moving in the sky, they go in a circular motion. I mean, were they correct? Why or why not? No, they weren't correct. You cannot be correct in science. So fast forward about 1800 years and Isaac Newton, right? So an apple fell on this very famous scientist's head, right? You can, now here was Newton's hypothesis, that his claim for the law of universal gravitation, that every mass attracts every other mass in the universe, and the gravitational force between the two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. So essentially, just this equation right here, right? So the larger the masses, the larger the gravitational pull. The farther those objects are away, well, the less that gravitational pull pulls on other objects. So is this a scientific claim? Well, yes, it is a scientific claim. There is a test for wrongness. So Newton's law of gravitation is so accurate that it was helped to discover the location of two different planets, those outer two ones, right? The Uranus and Neptune. But there was a problem, though, right? There was a small problem with Newton's theory. Mercury orbits the sun every 88 days, and as astronomers observed it, well, they noticed that by using Newton's math, the orbit was off by half a second. Mercury was arriving half a second earlier than Newton predicted every single orbit, right? And this added up, and scientists started to know this. Well, is this good enough? I mean, just think back to a game of chess where you don't know the rules, right? You're looking for something that doesn't make sense to see what that rule is. So another 300 years, Albert Einstein comes into the mix. Now, here's what Albert Einstein claimed. He claims that what we perceive as the force of gravity, in fact, arises from the curvature of space-time. So is this a scientific claim? Yes, it is a scientific claim. There is a test for wrongness. So how could you test it, right? So if Einstein wasn't wrong, then light, which doesn't have mass would be affected by gravity. Now, he used the sun, right? So if Einstein, if he was not wrong, right, what would happen is that light should bend around the sun. Now you can't see the sun at night, or sorry, you can't see the stars when the sun is out. But he used a solar eclipse, and he was going to see if the starlight traveled around or bent around the sun. So what they did was 6 months prior to the eclipse, they took a photo of the night sky, right, where the eclipse was gonna happen. 6 months later, when the Earth was on the other side of the sun, on May 29th, 1919, what they did was they took a photograph of the eclipse to see if the stars moved. And what you can see is that yes, right? If you compare those two photos, you can see that the starlight actually bent. Right? So this gave way for Einstein's theory of general relativity, which is a whole new way of thinking about gravity. Now, was he wrong? No, he wasn't wrong. But was he correct? No. In science, you can never be correct, right? You can never be correct. You're just not wrong. So the universe just doesn't have a box that can be opened, just like that black box experiment, to see if Einstein is correct. And 100 years later, well, one thing Einstein predicted was the existence of black holes. And in 2017, scientists captured the first image of a black hole, that proving Einstein wasn't wrong. But honestly, gravity still confines us. We can explain it, we can predict it, but we don't. We just don't understand like why mass bends space and time. So here are some final thoughts. There's just too much unknown in the universe to take a break from learning. Get out there and question everything.